COMSOL Multiphysics Lecture 9, Linear Buckling. In this lecture, we'll calculate the buckling mode of a cantilever beam with 10 meter long. And the material properties are Young's modulus of 3 times 10 to the 11th and Poisson ratio of 0.3. And the answer will be 3851 Newton. So we'll start drawing the 3D model. So in SolidWorks XY plane, we enter sketch mode and draw a square 50 by 50. And this is the cross-sectional area. And we'll extrude it into 10 meter. And I'll set the file on desktop. And for the first preparation step, I'll add in or load the software. And now I'll use COMSOL Live Link to connect the software. Now I'll open COMSOL in a separate window. And I'll open both softwares in two different windows and connect them with Live Link. Now, it is a 3D problem, and I'll choose solid mechanics. And in solid mechanics, as I said, there are different modules: statics, dynamics, natural frequencies, and buckling. And I'll choose linear buckling for this time, for this example. Now, for the first step, I'll load the geometry from SolidWorks and left button for rotating this geometry. This is the first step. The second step will be the material. And I choose a material from the library. Okay, I'll choose carbon steel, structural steel. And make sure that the geometry is connected to the material properties. And also, you have to change the numbers here, Young's modulus, into 300 times 10 to the 9th or 3 times 10 to the 11th Young's modulus, and Poisson ratio of 0.3. So this is the properties that is specified in the problem. Now, the material is the second step, so I mesh it. Since I'll check the result in numerical value, so I'll make it extra fine mesh and build a mesh. Now, for the fourth step, first of all, I'll give it a fixture, the fixed constraint, and I'll rotate this beam and fix it on this end and rotate back. Okay, for the load, boundary load, I'll choose this surface, and it will be a concentrated load. The type of load, the area on which the load will apply, the application surface, and the direction of the force, which is Z direction. I'll rotate it a bit so I can see that it is in Z direction, in positive Z direction. So I choose Z direction and enter 1 Newton in the Z direction, positive direction. Okay, for the positive direction, I can see it here. So I finished with the 4 steps for preprocessors. And before I run the study, make sure that you enter the number of modes that you are going to calculate, and it hides here, number of modes. And the software, the default is 1 mode, because in buckling analysis, the lowest mode is the most important, because it is the loading that will collapse the structure. But now, to compare with the result, I'll enter 8 mode to calculate, and then I'll compute. And the result can be compared with the theoretical value from mechanics of materials. So now I can compare the result. The first mode will be 3855, right? And the theoretical value is 3851. So it is very close. The values are correct. And you can see from here that, for example, the third mode, here the theoretical value is 120217, right? So it is about 120,000 Newton. And in the CAE analysis, it is only about 96,000. So it is 1/3 deviation. So about 30% error. So you can see here that the result is very different in higher mode, in the third and in the fourth mode. For example, in the fourth mode it is 1.9 million, and theoretical value will be 0.3 million, right? So it is a great difference. And how does that, why does that happen, and what is the correct one? You may wonder, is this the correct result, or is this the correct result? Because this is a result from mechanics of material. It is a theoretical result, and this is a CA result, and these are different. And the answer is that CA result is correct. It's the more correct one. It's a one that is close to reality. And why is that the theoretical value deviate from reality? The reason is that in structural mechanics, we often reduce the 3D beam into 1D line. For example, in mechanics of materials, we often represent the beam with a line, a 1D line. So the cross-section was ignored. That's why in higher mode, it is deviate from reality more and more. So make sure that if you are comparing theoretical value in linear buckling with the CAE value, make sure that you compare the lowest mode. And in higher mode, you should trust CAE instead of theoretical value, because theoretical value will deviate from reality in higher mode, because the beam is simplified into a line.